Have you ever wondered how a satellite can tell the difference between a forest and a farm? Or how scientists build models of our entire planet's climate? Well, it all boils down to something really fundamental: how different surfaces reflect light. Today, we're going to break down three key concepts that are at the heart of it all: reflectance, albedo, and this thing called BRDF.
So here's the game plan. We're going to start with the simplest idea, which is reflectance. And then we're going to build our way up. You'll see how each concept kind of layers on top of the last. So by the end, you'll have a really clear picture of how this all fits together.
All right, first up, reflectance. This is our ground floor, our starting point. It's really the most basic way you can think about light bouncing off an object. So just imagine for a second you're a satellite, a sensor, looking down at the Earth from one very specific spot. What exactly are you measuring? At its core, reflectance is just a simple fraction. We're asking a really simple question. Of all the light that hits a surface, what percentage of it bounces back in one specific direction, right towards our sensor? That's it. It's a single targeted measurement.
And it's really important to be clear on this. We're not talking about the heat an object gives off, like the warmth coming off an asphalt road. We are focused only on the light that's being reflected, kind of like how a mirror bounces a beam of light.
But what about the bigger picture, right? Measuring from just one direction doesn't really tell you the whole story. To capture all the light that's scattering off to the sides and everywhere else, we need a new idea. And that's where albedo comes in.
This right here is the key difference. Think of it like this. If reflectance is like pointing a laser-focused directional microphone at one person talking in a crowded room, albedo is like using a microphone that picks up all the sound in the entire room from every single direction. It's the total reflected energy over the whole hemisphere above a surface.
And this is exactly why albedo is such a big deal. I mean, if you want to understand how much of the sun's energy the Earth is absorbing versus how much it's reflecting back out into space, you absolutely need that total number. It's a critical value for climate models and for studying super-reflective surfaces like the polar ice caps.
Now we can get even more specific with albedo, which is pretty cool. It's not just about how much light is reflected. It also really matters where the incoming light is coming from in the first place.
Let's think about two perfect, kind of theoretical scenarios. Black sky albedo is what you'd measure on a perfectly clear day with no haze, where all the light is coming from a single point in the sky, the sun. White sky albedo is the total opposite. Imagine a completely overcast, gray day where the light is so scattered it seems to be coming from the entire sky all at once.
Of course, in the real world, most days aren't one extreme or the other, right? You've got direct sunlight and you've got that scattered light from the blue part of the sky. So the real-world albedo, which is sometimes called biohemispherical reflectance, is actually a weighted average of these two ideal conditions, the black sky and the white sky.
Okay, so we know the direction of the light source matters, and we know the direction of our sensor matters. I mean, think about a wet road at night. It looks totally different depending on where the car headlights are, right? So how do we describe all this complex behavior with math? Well, that is where the BRDF comes in.
So, the BRDF isn't just a single measurement like reflectance or albedo. It's the underlying rulebook. You can think of it as the complete recipe for a surface's reflective DNA. It basically defines how that surface is going to look from any angle under any lighting condition you can imagine.
And it does all this by being a function of four variables. You've got the vertical and horizontal angles for the incoming light, so where the sun is. And then you have the vertical and horizontal angles for the outgoing light, which is where you happen to be looking from. It's the whole geometric shebang.
So once you figure out the BRDF for, say, a patch of grass or a piece of concrete, you can then predict its albedo or its reflectance from any viewpoint on any day of the year. It's an incredibly powerful predictive tool. It's a game changer.
Now, it is really easy to get these last two concepts mixed up, but they are fundamentally different things. One is just a simple measurement, and the other is a whole complex function. Let's make this crystal clear. The key difference is right there in the units. Reflectance is just a simple ratio, reflected energy divided by incoming energy. So the units cancel out. It's unitless, just a percentage. But BRDF is defined as radiance, which is light traveling in one direction, over irradiance, which is light hitting a surface from all directions. This leaves it with units of per steradian, which is just a fancy way of measuring a cone of angles in 3D space. That angular part is what makes it a function, and not just a single number.
Okay, let's try a quick little thought experiment. There's this theoretical ideal surface called a Lambertian surface. It scatters light perfectly and equally in all directions, kind of like a perfectly matte piece of white paper. What do you think its BRDF would look like?
And the answer is a constant. It's just 1 divided by pi. For this perfect, simple case, that whole complex function that depends on 4 different angles just simplifies to a single, elegant number. This just shows that because the surface looks the same from every angle, its BRDF is constant.
So here's how it all stacks up. The BRDF is the most fundamental property at the very bottom. If you do the calculus and integrate it over the direction your sensor is looking, you get directional reflectance. Then, if you integrate that over every possible direction in the whole hemisphere, you get the albedo. It's a really beautiful hierarchy.